So the topic of today's video will be zeros and poles of a complex valued function, right? And you can recall from the calculus of a real function that what is the zero of a real valued function. That is a point, the value of x for which the function becomes zero, right? Or you can say geometrically the point where the function crosses the x-axis, right? For a real valued function. Okay. But here we'll be talking about the zeros of complex valued function. That is something different, right? And these poles are special type of singularities, right? As we have been discussing in the last videos, the singularities of a complex valued function, right? And if a function, complex valued function, has an isolated singularity at some point, suppose z equal to z naught. Isolated singularity means there is no other singularity in its neighborhood, right? You can think of an example of fz equal to 1 over z, right, where z equal to 0 is its isolated singularity, right? And whenever a function has an isolated singularity at z equal to z naught, then it can always be expressed in terms of positive as well as negative powers of z minus z naught, and we call it a Laurent series, right? So I will start with a Laurent series, as we discussed the Laurent series in our last video. So I will be contouring that Laurent series, right? Okay. Suppose fz has a Laurent series expansion about the point z equal to z naught, right, of the form fz is equal to summation a k z minus z naught k, where k starts from -1 to infinity, right? Or you can say minus infinity, or I should write minus k here, a minus k, and this will be 1 to infinity. Fine. It means that all the powers of z minus z naught are negative powers, right? And the other part, which is called analytic part, ak z minus z naught to the power k, where k starts from 0 to infinity, right? And this part is called principal part. Principal part, while this part is called analytic part, as all the terms inside this part, right, contain positive powers of z minus z naught, right? Positive powers indicates analytic part. Okay. So out of these two parts, this principal part has some significance, right? And we'll use the different cases of this principal part to understand the concept of singularity once again, right? However, you already know that a point z equal to z naught is called a singular point of a function if the function is takes value infinity at that point, right? Roughly we can say that, or we can say that the function is not analytic at that point, right? But we can classify a singularity, right, based on this principal part. This principal part of this Laurent series plays a significant role, right? And I will write those based on this principal part. Principal part of fz, right? A singularity can be, or we should say isolated singularity, because Laurent series is only possible if the singularity is an isolated singularity, right? And isolated, it means that there is no other singularity in its neighborhood, right? Isolated singularity can be classified as the first is a removable singularity. Right? Okay. And a function has a removable singularity at z equal to z naught if inside this principal part there is no term in its principal part, right? Means there are no negative powers of z minus z naught, right? Means the principal part is completely zero. Then you say that the singularity is a removable singularity, right? If this principal part, right, contains no terms or zero terms, right? For example, we can take a simplest example. If you take fz equal to sine z divided by z, right? And you want its Laurent series expansion first, right? So I will expand this function in positive or negative powers of z, because you can see that z equal to 0 is its singularity, right? Or you can say that z equal to 0 is the only possible singularity. If you put z equal to 0, you will get 0 by 0 form. However, on applying LH rule, you will get 1. That is a different case. But z equal to 0, we should check this function at z equal to 0. Otherwise, it is looking very good, right? Okay. So I will expand this. I will get, on expanding, z minus z cube by 3 factorial plus z to the power 5 by 5 factorial and so on, right? Then taking this 1 by z inside, I will get 1 minus z square over 3 factorial plus z to the power 4 over 5 factorial and so on, right? So you can see that there are no negative powers of z. It indicates that the principal part is completely 0, as we have written here. The principal part contains 0 terms, right? So there are no terms of negative powers of z. It indicates that the z equal to 0 is a removable singularity, right? Has a removable singularity at z equal to 0, right? As its expansion is giving no negative powers of z, right? So this is a very good example of removable singularity. And whenever we have a removable singularity at some point, then we can always convert this function into an analytic function, right? By defining this function at this point 0, right? If I define, I will write that here, defining f0 equal to 1. And why I have defined as f0 equal to 1, because I know that if I plug 0 here, then I will get 0 by 0 form, and on applying LH rule, I will get cos z over 1, and that cos 0 will become 1, right? Or you can say that if you see this expansion, right, if you plug z equal to 0 here, then this all of these terms will go to 0 and you will be left with 1. That's why we defined f of 0 equal to 1 in order to make this function, which has a removable singularity at z equal to 0, to an analytic function, right? Defining f0 equal to 1 will produce an analytic function, right? So a function with removable singularity at some point can be converted to an analytic function by properly defining it at that point, right? Okay. So second category is pole, right? And what is a pole? If the principal part contains finite number of terms. This part, principal part, contains finite number of terms, means there are finite powers of z minus, negative powers of z minus z naught, right? Say you have the maximum negative power of z minus z naught is m, right? Finite number of terms, right? Suppose z minus z naught to the power minus m is the highest term, or I should say highest degree term, right? In terms of negative integer, highest degree term in principal part, right? Then z equal to z naught is called a pole of order m, right? You can take an example of this, right? I will take this example again, and on doing some manipulation, I will get fz equal to sine z over z cube, right? So I have taken z cube as a denominator, and we'll see that has a pole at z equal to 0, obviously, right, of order m or 2 order 2, right? And why we are saying that z equal to 0 is a pole of this function and of order 2, because if I do the expansion of this fz, on expanding it I will get fz as fz equal to 1 over z cube and z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial, and so on, right? And taking this 1 by z cube inside the bracket, will have 1 over z square minus 1 over 3 factorial and then plus z square over 5 factorial minus z to the power 4 over 7 factorial, and so on, right? So this is the analytic part containing positive powers of z and a constant term, right? Obviously the constant term belongs to this analytic part for k equal to 0, right? And this is the only term which is containing the negative powers of z, and you can see that this is z to the power minus 2. If you take it in the numerator, it will be z to the power minus 2, and there are no other negative powers of z, or you can say that this is the highest degree term in negative powers, right? So fz has a pole of order 2 due to this 2, right? You can see this, right? That's why it has a pole at z equal to 0 of order 2, right? Had there been a term like 1 over z to the power 3, right, then we will say that it is a pole of order 3, right? Okay, now taking the third category, that is essential singularity. Essential singularity, right? And again, focusing on this principal part, right? If this principal part this is actually analytic part, right? This one. If the principal part of fz contains infinite number of terms, right? So on expansion, if you get infinite number of negative power terms, then we'll say that the singularity is an essential singularity, right? And taking its example, for example, the simplest example is e to the power 1 over z has an essential singularity at z equal to 0, right? If we expand this function, this is e to the power 1 by z, we will apply the exponential series, okay, as fz on expansion will give me 1 plus 1 by z plus 1 over z square by 2 factorial and 1 over z cube by 3 factorial, and so on, right? And you can see that there are infinite terms which are containing negative powers of z. This is z to the power minus 1, z to the power minus 2, z to the power minus 3, and so on, right? So the negative powers of z goes on increasing, and obviously there are infinite number of such terms containing negative powers of z, right? So z equal to 0 is an essential singularity of this function, right? So based on this principal part especially of Taylor series, the singularity, and one more thing, the singularity should be isolated singularity. An isolated singularity can be classified in removable singularity if there are no negative powers of z, or you can say that the principal part is completely 0, right? And then pole, if the principal part contains a finite number of terms, and essential singularity if the principal part contains infinite number of terms, right? Okay, then we'll go to this zeros, right? And you know that a complex function fz has a 0 at z equal to z naught if it becomes 0 at that point. Suppose you have a function sin z, Sin z is an analytic function, and you want to find its zeros, right? Then you will equate that sin z equal to 0, and obviously that will give me z is equal to n pi, right? An integral multiple of pi is a zero of function sin z, right? Those are called zeros, right? So I will write a formal definition of zero of an analytic function. Zeros. An analytic function fz has a zero at z equal to z naught of order m, right? And a zero has also an order, right? Okay, zero of order m if and only if f z naught equal to f dash z naught equal to f of double dash z naught equal to f m minus 1th derivative, right? This represents the derivative, m minus 1th derivative at z naught, all are 0, right? Means you say that function has a 0 at z equals z naught of order m if all of its derivatives up to m minus 1th order, 1 less than this number, all vanish at the points z equal to z naught, but the last derivative of mth order is not equal to 0, right? This is a formal definition of 0 of an analytic function, right? And we'll see why it is working in all cases, right? If I take an example, fz equal to, suppose I take sin z, right, or should I say sin square z, right, has a 0 at z equal to 0. Obviously you can see that if you plug z equal to 0 here, this will give you 0, right? But what is the order of this 0? Of order, I think 2, right? Okay. Solution or verification of this thing, right? I will use this standard definition, and according to this, if it has a 0 at z equal to 0, then if I find f dash z, it will give me 2 sin z cos z, or we can write it as for sine of 2z, right? And if I find its next derivative, that will be twice of cos 2z, etc., right? And I will put 0 in these f dash and f double dash clearly. f0, if you put 0 here, you will get sin 0 equal to 0. If you put 0 here in its first derivative, it will also give 0. But if you put 0 in its second derivative, you will get 2, that is not equal to 0, right? And you can say that this definition, according to this definition, it must have a pole at, it must have a 0 at z equal to 0 of order 2, okay, right? And we have one more theorem. I have to rub that first, right? Theorem, right? And the theorem says that a function analytic at point z equal to z naught, obviously z equal to z, if f z equal to z naught is a 0 of a function fz, then it cannot be a singularity of fz, right? I should write fz here. A function fz analytic at z equal to z naught has a 0 at z equal to z naught if and only if this fz can be written in this form, z minus z naught to the power m. I should write 0 at z equal to z naught of order m, right? Okay. If and only if is this fz can be written in this form multiplied by some other function, let me write it as gz, right, where gz is analytic at z equal to z naught and gz naught is not equal to 0, right. So another way of looking at the 0 of a complex function which is analytic at a point z equal to z naught is that if you can express that function in this form, right, z minus z naught to the power m and gz, where gz should not be equal to 0 at that point, right, and it should be an analytic function at z equal to z naught, then you will say that the function has a 0 at z equal to z naught of order m, right. So after this you should, okay. So this result is obvious from that definition, right. I will use that definition to derive this result, right. Why is it important? And this result of course is very important in searching for the order of a 0 in numericals, right. We will use that or this one, and sometimes it will be handy to use this formula, right. Okay, so we will give a small proof for this. And since since function is analytic at z equal to z naught, and you know that if a function is analytic at some point, then it can always be expressed in positive powers of z minus z naught, right, in some disk centered at z equal to z naught, and that gives rise to Taylor series. There is a difference between Taylor's and Laurent series. While in Taylor series all powers of z minus z naught are positive, and in Laurent series some powers of z minus z naught may be negative, or more powers may be negative, right. So I will be using Taylor series at this point because we know that function is analytic at this point, right. Had this been the singularity of this function, then I would have used that Laurent series, right. Okay. Since fz is analytic at z equal to z naught, right, therefore its Taylor's expansion about z equal to z naught in some disk, right, okay, will be is of this form. Fz equal to, if you remember the formula for Taylor series centered at z equal to z naught, then this is the formula fz equal to f of z naught plus f dash z naught over 1 factorial, okay, z minus z naught to the power 1 and f double dash z naught divided by 2 factorial z minus z naught whole square and so on plus f n minus 1th derivative at z naught over n minus 1 factorial z minus z naught to the power n minus 1, and then writing f nth derivative evaluated at z naught divided by n factorial z minus z naught to the power n, and then f n plus 1th derivative at z naught over n plus 1 factorial and z minus z naught to the power n plus 1 and so on, right. So this is the Taylor's expansion of fz about the point z equal to z naught, right. Okay, and now I will use that formal definition, right. You are assuming that z equal to z naught is a 0 of order m, right. So if I have written m here, okay, so I should write m minus 1, and this should be m, right, m, and this is also m, right, according to this m. Okay, since this point is a 0 of order m, it means that using that definition f of z naught equal to f dash of z naught equal to f double dash of z naught up to m minus 1th derivative at z naught, all of them will be equal to 0 according to that definition, right. If you say that a function is a 0 at z equal to z naught of order m, then all its derivatives up to m minus 1th derivatives at 0 will vanish, right? But the mth derivative of m evaluated at z naught will not be equal to 0, of course, right? So I will be using this information here in my series, right? So in that case, all of these terms up to, I think, m minus 1, this is my m minus 1, up to this term will vanish, and we'll be having these terms, mth derivative terms onwards, right? Therefore, fz will become, all of these terms up to m minus 1th derivative will become 0 due to this. Then I will be left with these terms, right? Okay, f mth derivative evaluated at z naught over m factorial z minus z naught to the power m, this is m, and this is m plus 1, fine, and this is also m, right? Plus m plus 1th derivative evaluated at z naught over m plus 1 factorial and z minus z naught to the power m plus 1, and so on, right? So again, take z minus z naught to the power m common, right? And inside bracket we will be having mth derivative at z naught over m factorial plus m plus 1th derivative at z naught m plus 1 factorial, and this will be z minus z naught plus so on, right? So you see that we have this factor here as we wanted. See this, your fz is eventually equal to z minus z naught to the power m, right? And this is your gz. You should write this whole function as gz, and this gz has this special property. What property? Gz is analytic at this point. You see that since all of these terms are positive powers of z minus z naught, or you should say non-negative powers, because it's a constant term also, right? All of these terms in this series are non-negative powers of z minus z naught. So you can say that this function gz, right, is analytic at point z equal to z naught, right? Okay, and at z naught it is not equal to 0. If I plug z naught here in place of z, if I plug z naught, then all of these terms after this term, all of them go to 0, and we'll be left with this one, right? So it is a verification, right? Or fz equal to z minus z naught to the power m. I am writing this as gz, this whole series, right? Such that you can see that gz is analytic at z equal to z naught, and you should know the reason why I am writing this. Gz is analytic at z equal to z naught because it is containing positive powers of z minus z naught, that's why. And g z naught, if I put z naught here, then I will be getting mth derivative at z naught over m factorial, and that is obviously not equal to 0. And why I am writing that this is not equal to 0, right? The reason is that this numerator is not equal to 0, and you can see from here there is that, right? Okay, so this is a small proof for this theorem, right? Okay, and based on this theorem we can write a result for pole also, right? In this video we will be interested in finding the pole, right? However, we have three types of singularities. One is the removable singularity, essential singularity, and this pole. So pole will be your main focus, right? Okay, so we should add a remark here. A remark between the relationship of zeros and poles, right? You can say that zeros and poles are interrelated somehow. Okay, suppose we have function fz equal to hz over gz, right? A rational function hz over gz, right? is a function, right? Okay. Then poles, then fz, this function fz, rational function, has a pole at z equal to z naught, right, of order m, if and only if gz has a 0 at z equal to z naught of order m, right? So you have a rational function, and since you are having a rational function of type 1 over z, like, okay, then it must have a pole, right? Okay, so we'll say that this function has a pole at this point z naught of order m, if and only if the denominator function, the gz, has a 0 at that point of the same order, right? And provided, the important point is that provided at this point this numerator should not vanish, right, as well as this numerator should be analytic at this point, right? So there's a danger also, right? Do not put directly this denominator equal to 0 in order to find the order of a pole, right? You should remember that. I will write that, provided the numerator function hz is analytic at z equal to z naught and it is not equal to 0 at that point, right? So keep in mind this additional condition. Okay, so finding a pole for rational function will be ultimately equal to finding the 0 of its denominator function, provided that the numerator function is not equal to 0 at that point and it should be analytic at that point, right? Okay, so we'll use these methods to find the order of a pole or order of a 0. We have this theorem also, or we can use this formal definition to find the order of a 0, right? And in order to find the order of a pole, we'll use again this result, or we'll rely on that Laurent's expansion. Remember that if a Laurent's expansion has a principal part, means all negative powers of z minus z naught, and there are finite number of terms in its principal part, then we will say a pole, right? And its order is given by the highest negative power of z minus z naught, right? So we'll be using all of these facts wherever applicable, right? Example number 1, find the zeros of the following functions, right? Also state their orders. Also state its order, their orders, right? So you have to find the zeros of a function. You will be given a function, complex valued function, and you have to find its 0 with its order, right? So first example I should take, if fz is equal to e to the power z minus 1, right? Okay, and okay, solution. And since you need to find its zeros, right, you will substitute this function equal to 0, put this function equal to 0, you will get e to the power z equal to 1, right? Okay, and you know that e to the power z is equal to e to the power, however in real calculus if you have e to the power x here, then you should have written e to the power 0 only, right? But since you are dealing with a complex number, then this is not the only choice, right? Actual exponent should be 2n pi eta, right? And how it appeared, I can write it as this. 1 can be written as cos 2n pi. You know that cos even multiple of pi is equal to 1, cos 0 1, cos 2 pi 1, cos 4 pi equal to 1, and you know that sine of 2n pi is equal to 0. Any multiple of pi, which is an angle of sine, equal to 0. So 1 can be written as 1 plus iota 0, right, in complex notation, and this n is actually an integer, right? Negative value as well as positive value, both are allowed. So ultimately it will be e to the power iota theta. You can see that this is your theta, cos theta plus iota sin theta, so it will be e to the power iota theta, right? So this is the more general value of 1, right? Do not write e to the power 0, as you have a habit of writing 1 equal to e to the power 0 in real function, in case of real function, okay, where this n is an integer, right? Now you can compare the exponents, that will give you z equal to 2n pi iota, and n is an integer, right? So these are the zeros of this function, and they are infinitely many. If you put n equal to 0, 1, 2, 3, you will get 0, pi, 2 pi iota, 4 pi iota, 6 pi iota, as well as negative values are also there, minus of 2 pi iota, minus 4 pi iota. So there will be infinite number of zeros, right? And what will be their order, right? Because you need their order also, right? So I will find their order. I will differentiate this. I will use the formal definition to find the order, or you can use the series extension also. I am using the formal definition first, then I will be using the theorem, right? Okay. To find the order of 0 at z equal to 2n pi iota and belonging to z. I am taking all of them, right? I am not taking only one 0. I have written all of the zeros, right? Okay. We see that if I find f dash z, differentiation of this thing, that will be e to the power z, and obviously f double dash, all of them will be e to the power z, etc., right? And if I put f inside f my 0, what is my 0? 2n pi iota, then it will become e to the power 2n pi iota minus 1, that will be obviously equal to 0, right? Okay. F dash 2n pi iota, what if I put this 0 in my derivative, right? Then it will become e to the power 2n pi iota, then it will become 1, right? And that is obviously not equal to 0. So this is the first derivative which is not equal to 0, right? It means that z equal to 2n pi iota is a 0 of order 1. Why 1? Because it is the first derivative, right? Therefore z equal to 2n pi iota, right, and belonging to z is a 0 of order 1, right? And if it has a 0 of order 1, then we have a special name, it is called simple 0, right? Simple 0, right? Take another example, B, fz equal to e to the power z and z minus 1, right? So we have this exponential function multiplied by z minus 1 factor, right? Okay. Or I should write z only, that will be good. If I take z, e to the power z multiplied by z, okay? No, e to the power z minus 1 multiplied by z, then it will become complicated, right? Okay. Solution. In order to find its zeros, you will put this function equal to 0, and be careful at this point. This will give you z equal to 0, right? And then e to the power z equal to 1, right? And e to the power z equal to 1 will eventually give you z equal to 2n pi iota and belong to z. I am writing that directly, right? Implies z equal to 0 and z equal to 2n pi iota and belonging to z, right? And you can see that if you put, because 0 belong to this set z, if you put 0, you will get z equal to 0 also. So z equal to 0 will be available twice, right? And for n equal to 1, you will have 2 pi iota, 4 pi iota, and so on, right? So the special treatment should be given to the 0 z equal to 0. Why? Because it has appeared twice, from here from this function and from this exponential function, right? So we'll treat z equal to 0 as a special 0 and find its order, and the rest of the zeros will be treated separately, right? So first I will be picking z equal to 0, which appeared twice here and here, right? Okay. Now z equal to 0 is a 0 of order, and I'm leaving that. What is its order? I will find that order. Okay. As f dash, first we'll find f dash, that will be z times e to the power z plus e to the power z minus 1. This will be its derivative. Second derivative, f double dash z, that will be z e to the power z and then e to the power z and then e to the power z. I think it will become twice of e to the power z, right? Okay. Etc. Since we see that if I put 0 in the function here, I'm checking at z equal to 0. If I put 0 here, then obviously it will become 0. And if I put 0 in its first derivative, then it will become 0, 1, minus 1, 0, right? Means up to first derivative the function is 0, but its second derivative, this one, evaluated at z equal to 0 is not equal to 0, it is actually equal to 2, right? So we can say that z equal to 0 is a pole of order 2, because this is the first non-vanishing derivative at z equal to 0, right? Is a 0 of order 2, and this is the reason, right? So we have used that formal definition, right? There is an alternative also. If you, rather using these derivative property, you just expand this function e to the power z, right? And e to the power z has expansion 1 plus z square by 2 factorial and so on, right? Then 1 and 1 will be cancelled, right? And you take z common out of this series, and it will be of the form z square multiplied by 1 plus something something, right? And then you will use that theorem, means of a function as written in this form, z to the power n multiplied by gz, right? So obviously the outer function after expansion will be z square, and indicating that it is 0 of order 2, right? Should I write it here in short using that series? Fz equal to z times 1 plus z square by 2 factorial and so on, right? Minus 1 using expansion for this thing, then 1 and 1 will be cancelled, z will be out, it will become z square, and inside we'll have 1 plus z by 2 factorial and so on, right? You can say that this is z square into gz, right? And this, obviously this gz has all positive or non-negative powers of z, and it will be an analytic function, and it is not equal to 0 at z equal to 0. If you put z equal to 0 here, you will get 1, right? Where gz is analytic and g0 is not equal to 0, right? So you can say that this is the reason, means both of them are valid reasons to write this order 2. Either you can use this one or this one, right? This is using the formal definition, this is using the theorem, right? Now we'll come back to the other zeros, means z equal to 2n pi iota, where n is not equal to 0, right? Now z is equal to 2n pi iota, where n is any integer other than 0. It means you have deleted 0 because you have considered that case separately already, right? So this time I will be taking an integer which is non-zero, right? Is a 0 of order, I will leave that blank, what will be its order, we will see that, okay? Now we find f dash and f double dash are available to us, right? I will plug this 0 in my f dash and f double dash, right? As f evaluated at 2n pi iota, right? If you put 2n pi iota here, obviously we will get 0. Why? Because you can see that z equal to 2n pi iota is obtained on equating this function equal to 0, right? So do not actually check this step. F will always be 0 as it's 0. That is obvious from the definition. But what about its derivative? Okay, is equal to 0. But if I plug this 2n pi eta in its first derivative, where is its first derivative? This is the first derivative. You just put 2n pi eta here, right? If you put 2n pi eta, it will become, I will write that 2n pi eta e to the power 2n pi eta, and this will be e to the power 2n pi eta minus 1. You can see that this e to the power 2n pi eta is actually equal to 1. These two terms will be cancelled out, and we will be left with 2n pi eta, which is not equal to 0 if and only if this n is a non-zero, and obviously n is a non-zero, right? Not equal to 0 for all values of n belonging to z or subtracted 0 from it, right? So we can say that its first derivative is not equal to 0, so all of these zeros are simple zeros, right? Therefore z equal to 2n pi eta, n belonging to z, 0 is deleted from it, are simple zeros. So in this example we have to treat this z equal to 0 separately. Why? Because this 0, z equal to 0, is obtained from this function as well as this function. So whenever you have this kind of situation, you treat that 0 separately, right? Okay, let me take an example of poles, right? Example number 3. Find the type of singularity or nature of singularity, type of singularity of the following functions, right? Part A, if I write f z equal to e to the power z minus 1 over z square, right? Okay, solution, right? We have to search for its singularity, right? And obviously, as we have been doing in our last videos, the singularity is obtained by equating the denominator to 0, right? But there is a condition there that the numerator should not be equal to at that point. If I equate this denominator equal to 0, I will get z equal to 0, obviously, right? But at that z equal to 0, the numerator is also going to 0, right? So do not use that process in order to find the singularity of a function whenever you have your numerator going to 0 at that point. So I will rely on the basic, very basic thing, Laurent series, right? I will expand this function by Laurent series, right? And we'll see what happens. Okay, so expanding by Laurent series, we will see that 1 over z square, and this e to the power z will be expanded as 1 plus z square by 2 factorial, so on, and we have then minus 1 here also, right? And 1 and 1 will be cancelled out, right? And this z square will go inside, it will become 1 over z plus 1 by 2 factorial, and the other term will be, I think, z by 3 factorial, and so on, right? So ultimately we have a Laurent's expansion, and why I am calling it Laurent's, because see this term, negative power of z, and all of these terms are non-negative powers of z. So this is corresponding to analytic part of Laurent series, and this is for principal part. And now comes that point, focus on the principal part. If you focus on this principal part, you see that there's only one term, means finite number of terms, and this indicates that z equal to 0 is a pole of the, and why I am saying z equal to 0 only, because I know that z equal to 0 was the problematic point from here, right? So z equal to 0 is the pole of order 1. Why of order 1? Because see the power, z to the power 1, negative power is 1, maximum negative power is 1, right? Since the principal part contains, right, finite terms, therefore z equal to 0 is a pole of order 1. And why 1? Because the most negative power is z to the power 1, right? And that's why we call it simple pole, right? Another example B, if I take fz equal to 1 over e to the power z plus 1, right? Okay, I think that will not give me pole because negative, okay, cos minus 1 pi, yeah, okay, fine. So in order to find its singularity, it is clear that I can use that process putting denominator equal to 0, right? And you see that this function 1, this is a constant, right? So there will be no danger as occurred in this situation from getting 0 from here in the denominator and plugging that 0 here will produce 0 in the numerator. So that is not the situation with this example, right? So I will put denominator equal to 0 in order to obtain the singularity, our previous method. Okay, that will give me e to the power z equal to minus 1, right? And now again you can write this minus 1 as cos has minus 1 if odd multiple of pi, right? So I will write that cos 2n plus 1 pi, right? Because if I put 0, that is fine. Okay, plus eta sine 2n plus 1 pi. You can see that if you plug n integer, right, put n equal to 0, you will get cos pi, that is minus 1, and this will be 0. N equal to 1, that will be cos 3 pi, right? Again that will be minus 1 and 0 and so on. Then it can be written as e to the power z equal to e to the power eta theta. So this time theta is this 2n plus 1 pi, and that will give you z equal to 2, I think eta will be also there, z equal to this thing, right? Okay, 2 n plus 1 eta pi, and where n is your integer, right? So these are the poles, and remember that fz is a rational function, right? And as we said that poles of a rational function, if a rational function is of the form fz equal to hz upon gz, right, are given by such function, poles of such function are given by zeros of the denominator, provided the numerator is analytic at those points. You can check that at all these points this is constant function is obviously analytic and is non-zero at these points, right? So I'm using that remark I have written here, right? Okay, so these are the poles, right? Are poles, and if they are poles, then certainly there will be some order of these poles. And in order to find the order of these poles, what I will do, I will find the order of zeros of my function gz. Actually this is hz over gz, and what I have done, I have equated gz equal to 0, right? And we found that these are the zeros of gz, which implies that these will be the poles of fz, right? And if I am able to find the order of these zeros of gz, right, then I will be automatically able to find the order of poles of fz, right? Means finding the order of a zero of the denominator function gz is automatically equal to the finding the order of poles of the complete function, rational function fz, right? So what I will do, I will apply that formal definition of zeros by finding its derivative, right? Okay, now I will differentiate this g dash and so on. Also are poles of, these are poles of this fz, however these are zeros of gz, right? So also doing differentiation, g dash z will be e to the power z, and g double dash will be automatically equal to e to the power z, etc., etc., right? And now you see that if you plug this 0 of this gz in g and g dash as g 2n plus 1 pi eta is equal to 0, right? But g dash 2n plus 1 pi eta is not equal to 0, right? Therefore you can say that g z has a 0 of order 1, because the first derivative is non-vanishing. And if we say that this denominator function gz has a 0 of order 1, it automatically implies that this fz has a simple pole, right? I will write that here. Therefore fz has a simple pole. At z equal to 2n plus 1 pi eta n belonging to z. Okay, so this is it for this video, zeros and poles, right? So you maybe are able to understand the theory about zeros and poles, the idea about finding the zeros and poles and why they are related, right? Especially when we have a rational function, right? We will be doing some more examples of zeros and poles in our next video. For this video, thanks.